Um, Good morning, everybody. My name is Renan. Today I will talk about this work I did in collaboration with my advisor, Luis Crispino, and Andreu Massó, Flávio Bombatinho, and Gonzalo Alma from University of Valencia in Spain. The idea of this work is to introduce this new kind of compact object that we call it bounded universe. It's similar to a wormhole because it has a throat, so it connects to different universes by this bridge. But different from usual wormholes, the outer universe is asymptotically flat, but the internal region is asymptotically bounded. So the area radius of it is goes to a finite value. Here I put a representation of it. As you can see, the outer universe is asymptotically flat. It basically is the Alice wormhole, but the internal region is a sort of bubble. Well, it's not the only configuration we created, but this can summarize the idea of our objects. And as you see, introducing this kind of boundedness inside will introduce a lot of new phenomenology, such as trapped orbits and trapped modes inside it. So, since we are modifying a wormhole, let me first say a few words about it. Wormholes are these interesting exotic objects. Unfortunately, we don't have now a clear formation of these objects. We don't know what kind of matter can actually form this via gravitational collapse or something like this. But they are gaining increasing attention in the literature nowadays, both from theoretical perspective, but also from observational perspective, since they can share a lot of similarities with black holes, but also present an entirely new phenomenology. For example, echoes. I think most of you know what is it, and we'll talk about it later. Usually, wormholes are defined by this minimum in the area radius of them, and we call this structure a throat. And here I put an example, the Alice-Burnikov wormhole, that is very similar to the Minkowski spacetime, but the spherical sector of it has this minimum. When x is equal 0, we have a minimum in the our spherical sector. It has a parabolic behavior then. Okay. But wormholes are not the only objects with throats we can find in the literature. For example, we can also find throats inside black holes, for example, with black-bound solutions, and maybe more interesting, baby universes. The idea of a baby universe is basically expanding universe inside a black hole. And curiously, last year, the group from Valencia University, basically with Andreu Massó, Nico, Tony, and Gonzalo, they found that it's possible in Palatini FFR to have a dynamical formation of a baby universe by considering a Broca star collapsing. Then, after the formation of the black hole, the event horizon, inside it is formed a sort of bubble, expanding bubble, and its expansion is exponential. But unfortunately, the throat in this case, or let's say the umbilical cord, because it's a baby universe connected to a parent universe, is covered by the horizon. So extracting information from it is basically impossible, because we cannot have any information from a region that is causally disconnected. So in order to bypass this kind of problem, we thought, okay, so let's try to build something that is more or less similar to it. It is also a bounded region inside a throat, but it does not have an event horizon. So we constructed something that is more or less like it, It is static, it's not expanding like their solution, but it shares this similarity that it is bounded inside. And we want to investigate what kind of phenomenology we can see from something that is bounded inside the wormhole. Basically, we looked for two assumptions in the area radius. We consider that it has indeed a throat, and this throat is smooth. So we have a local minimum, and we require that at least the second derivative of it is continuous at the throat. And also in the asymptotic internal region, we have that the area radius is asymptotically bounded. So the R of X goes to this asymptotic value capital R. Of course, we have a lot of functions that can obey these two assumptions. We choose this particular toy model that has two parameters, the capital R, that is the asymptotic radius, and this little c, that controls how fast the throat departs from a parabola. So basically, near the throat, when capital R is really close to 0, it is basically the same. But if we go further inside the wormhole, it goes to the asymptotic value. And as we can see, if capital R is equal 0, basically the internal region shrinks to, it's basically a bubble, and the asymptotic radius shrinks to 0. As we can see here, we have basically these two configurations. When capital R is equal 0, we have this bubble, and when capital R is different from 0, we have this thing that the internal region is replaced by a two-sphere core. As you can see, in the case when capital R is equal 0, the space-time volume inside the wormhole is finite. But in the case when capital R is different from 0, it's not true. The internal region has diverging space-time volume. Well, in the left case, when capital R is equal 0, all the curvature invariants diverge in the asymptotic infinity. It's not a problem, actually, because as you see, the geodesics are complete, and the only geodesic that can reach this region reaches in an infinite affine parameter. So this region is actually inaccessible to an observer. And in the other case, when capital R is different from 0, the curvature scalars are finite and go to the values of a two-sphere. Well, it's we expected it since the asymptotic flat region was replaced by a two-sphere core. So we expected that the curvature invariants inside go to the ones of a two-sphere. Okay, so let me discuss some phenomenology we can study from these objects. As I said, we studied the geodesic structure of it. We saw that all the geodesic, regardless the values of the parameters, are complete, and it is important, in particular for the R equals 0 case, because we have a divergency in the curvature scalars inside, but the only geodesic that can actually reach this region is a geodesic that is in radial motion. But this radial geodesic can only reach it in an infinite affine time. And interestingly, when capital R is equal 0, the effective potential has exponential growth. And we see that, and we can approximate this exponential growth by this expression. And we see that any photon with, for example, impact parameter different from 0, so a geodesic that is in non-radial motion will at some point face the effective potential and suffer a bounce and be scattered to the outer universe. So, for example, we have a congruence of geodesics impinging from the outer universe, crossing the wormhole throat, and in some point inside the bounded universe, it will suffer a bounce and will scatter back to the outer universe. Here, for example, I'm representing it. We have some geodesics coming from the outer universe. They cross the wormhole throat, propagate inside, suffer a bounce, and are scattered back to the outer universe. When capital R is different from 0, we have a different behavior. The geodesics enter, cross the throat, and propagate in the internal region forever. As you can see, they start to species of helicoidal. I don't know if it's actually helicoidal, but it's something like this. Here, basically, the geodesics will spin forever in this geosphere core. Well, we also studied the stability of circular orbits because it is important to see if we can find stable circular orbits in these bounded configurations. Because when we study the Alice wormhole case, we don't have any stable circular orbits there. In the Alice wormhole case, that first wormhole I showed you, the only circular orbits we have is an unstable one at the throat, even if it is a light ring or a unstable time-like geodesic. But here, we notice that when we introduce the boundness inside, we have also a local maximum in the area radius. Then this local maximum, when we investigated from the Lyapunov exponents, we saw that this local maximum corresponds to stable circular orbits, both for photons and for time-like geodesics. This is interesting because now we have a stable light ring inside, and this stable light ring will be important when we investigate, for example, modes that perturbations in this configuration, and this this stable light ring will reflect in echoes in this structure. Well, so the importance of this study of the stability is that now in the bounded configuration, we can have basically 3 kinds of circular orbits. At the throat, we have the standard unstable circular orbits present in the Alice wormhole case. In the belly of the wormhole, let's say, we have these stable circular orbits, and when capital R is different from 0, we have this asymptotically marginally stable circular orbit. This happens when the Lyapunov exponent is equal 0. It's basically it. Okay, so let me just show here if we propagate, if we, for example, consider a photon inside the bounded universe, we have these trapped orbits inside. They can't be scattered to the outer infinity if these photons have an impact parameter in this region. They will propagate forever inside and do this sort of trapped orbit. Okay, so this indicates that we can also have trapped perturbations inside, and we investigated it. We computed basically the dynamics of a scalar field, and we evolved a Gaussian scalar package. We are considering a Gaussian scalar package impinging from more or less 20 in these units of x, and this Gaussian wave package will interact with the bounded universe. Part of it, when face the light ring, let's say, will ring it and will measure the quasi-normal modes. Part of it will be transmitted inside and be quasi-trapped in this cavity. These quasi-trapped perturbations we will measure as the echoes of this object. So And the dashed line is basically the time profile of the usual Alice wormhole. The Alice wormhole, as you know, has only a single peak in the effective potential of the scalar wave. So we don't have any cavity there. Since we don't have a cavity, we don't expect the presence of echoes. So we have this tail in the quasi-normal mode spectrum. But when we introduce the boundness inside, we create this cavity, and this cavity can trap perturbations. And as we can see, now we have this this very different behavior. Since the throat is basically the same in both cases, the quasi-normal modes are the same. The quasi-normal modes are basically this, I don't know if here. The quasi-normal modes are related with this part here, and it is related with the ringing of the light ring, while this part here is related with the modes that are quasi-trapped in the cavity. We could estimate the period of these echoes by computing the effective size of this cavity. Here I didn't put the numerical values, but you can find the values on archive later. And just to finish, let me show you what happens when we change the parameters. When we change the parameter C, basically we are making that bubble smaller. So the frequency of the echoes will increase when we increase the value of C. And when we consider different values of capital R, basically when capital R is equal to 0, have the bubble, and when capital R is different from 0, have that thing that is asymptotic, that is sphere core. And when we increase the value of the asymptotic internal region, basically we restore the Alice wormhole behavior. We have this, as you can see, the spectrum is restored. Well, this is my final remarks. I think we don't have time to. Well, I leave it with you.
So thanks for the talk. Do you think the baby universe shares some similarities with the beginning of our universe, because they are expanding and so on?
Yeah, I think since at least this model of baby universe that I presented in the very beginning of the talk, the growth is exponential, and maybe it can be used to model the inflation period of the early universe. So I don't have sure, because I never studied, but since it has exponential growth, maybe it can be related with the inflationary epoch of the universe. I don't know.
Thank you, Renan. So you mentioned that, so can you go back a little bit? Yeah, there. So you mentioned that the first decay is due to a part of the quasi-normal mode, but this is actually a quasi-normal mode of the system, or?
No, here, I will go back here to this image. Okay, so I don't know, can I go there, maybe? Okay. So imagine that you have a wave package here in this region. The wave package will face this. Okay, the wave package will interact with the maximum of this local maximum here. The excitation of this local maximum will measure as the quasi-normal mode, and it is the first bounce of the wave package. So the wave package will interact with the effective potential. The first bounce related with this first peak, we will measure it as the quasi-normal mode spectrum, basically. But we have more interactions because then the wave packet will cross the wormhole throat and then suffer a series of reflections inside. And the series of reflections inside are these echoes here. But the very first, not the first bump. The first bump is it's related with the is the prompt, right? But the second is the.
But my question is that, so for compact objects, usually this first decay is not an exact mode of your system, right? You have, so if you compute the frequencies, this first decay is what mimics the black hole. So I'm curious that you find this frequency in this function?
No, we didn't compute, but the point is that we analyzed configurations that are very similar to the Alice wormhole near the throat. And near the throat, the spectrum is quite the same. Maybe if we use Prony, we can extract, and I think we will extract the same values of the Alice wormhole.
Okay, thank you.
Any final question? So let me just ask something to clarify. So the modification you've done of the Alice wormhole, you postulated the geometry, or does it solve any field equations? You just postulated it. Did you think about trying to make it some solution of something? Because you started with some solutions of the Palatini gravity, the baby universes, right?
Well, of course, we could, for example, consider there is a solution of Einstein's equation, but the model will be a completely weird fluid. We didn't try to find a solution of any modified gravity theory that represents something like this, because the original work that what they find it is completely awful, so it's weird. So it's difficult to find solutions that just similar to. And here it's just a toy model to represent something similar to that.
Okay, so let's thank Renan again. And with this, we close the session. It was, let's say, an interesting session for various reasons. And thank all the speakers of the session, the ones that managed to give their talks and the ones that did not manage to give their talks. So thank you very much to all.